Okay, let's go for chapter 10 anyway about the spring anyway. In this chapter, we have four characteristics of springs anyway. Number one, we're gonna have the spring like coil spring of the compressor coil springs anyway. And second, we're gonna have the compressor spring in order to have a some kind of tensile springs anyway. And third, we're gonna have a twisting spring. And fourth, we're gonna have a leaf springs typically. So therefore, let's go for one by one anyway. Number one, we have the mechanical properties of the spring valve. We're gonna talk about the spring valve alone anyway. So therefore, typically we have a spring valve. When we talk about spring valves anyway, we have a valve, things like that, to make a spring. Typically, the spring valve is gonna have a sigma u respectively. We're gonna have a sigma u equal to a is a constant over t to the power of x, and then the tau sub n is going to be the shear endurance strength to the equal to b over d to the powers of y respectively, where the a, b, x, and y can be able to determine from the table 10.1 respectively. So therefore, you may figure out in the material in table 10.1, we can classify in the first three lines is going to be the typical type of the steel that what we typically can find it. You may figure out we have three types of vials, things like that. We have ASTM, of course, is going to be the brittle materials all the way. This typically can be able to find in our countries. Number one is easy to find, and then number two, music valves, things like that, is going to be typically find it in Thailand, and then oil simple well it's going to be kind of hard to find it. But for the wild swing steel, CRV, common silicon steel, things like that, it's very difficult to find it in Thailand, things like that. And then the last line, stainless steel, is can be able to find in Thailand. It's very popular to work out with this kind of steel in Thailand, to work in the water, things like that, in a soak in the some kind of like a fluid, whatever, things like that. A lot of employment for the stainless steel in some kind of like fluid, things like that, most of the time. X, Y, A, and B is going to be a constant, things like that can be determined for the equation to determine for sigma u and tau sub n respectively. Okay, so therefore, if we got those kind of thing, we can determine the E term, the Young modulus, and the G term in table 1. For the stainless steel, we're going to have an E term and G term respectively. And then for the tau sub y, for 10.1, and for the stainless steel, we have a tau sub y of 0.47 of sigma u respectively. And then let's go for number one, the hierarchical compression coil spring. Okay, so let's get started with this type of coil spring anyway. This type of coil spring we just employ a lot with this coil spring for a compressive matters. We employ a lot with the coil spring of this type for automotive things like that. We have a coil look like that. We have a diameter of the capital D like that. We have a diameter of the spring wire of the small d look like that. And then we have a lambda. Okay, that's this the angle of the coil, things like that. Okay, and then therefore we apply the force of F applied on the coil spring, look like that. Okay, and then if we just move the force of F to be at right here, okay, at the spring valve. Okay, so therefore we can be able to just look like that. Okay, so therefore valve formulation can be able to just show you the terms of the tau gonna be equal to k 8 times f times d over pi d to the power of third, things like that, or k times 8 times f times c, and k is equal to things like that. And the most importantly, it's going to be the c term is going to be over the d, the capital D over d then. Okay, you may figure out the d over small d, things like that is mean. Okay, The D term here, okay, gonna be show some characterized on that is gonna be the spring index here, okay. The spring index is gonna be recommended to be 5 to 10, not less than 3, things like that. It seems to me if D is great, okay, is huge, things like that, it's mean, so the capital D is gonna be more than, okay. So therefore, the D term is gonna be down, okay. D is gonna be large, right? The capital D is gonna be large. So therefore, the coin spring is gonna be short, okay, and large, things like that, okay. If C is small, so therefore the coin spring is gonna be long, okay, gonna be long, things like that. Okay, so therefore, this kind of characterized gonna be the shape of the C term is gonna look like that. Okay, and then F gonna be the axial load, and D is gonna be spring wound, and D is gonna be the mean diameter. Is K is gonna be the wound factor, and K sub C is gonna be the term of curvature correction factor, and K sub S is gonna be shear stress correction factor respectively. Okay, and then okay, lambda there is gonna be the pitch angle. Okay, the P is gonna be the pitch. Pitch is gonna be the distance apart from one coin spring to another coin spring. Look like that. Okay, so therefore this is the things that what is show you up there. So that's why this formulation, Mr. Wild said, lambda is gonna be quite valid. Okay, with a small angle less than 12 degrees respectively. Okay. So therefore, based on this, okay, the terms of delta, if we just represent the force of F, okay, and the delta term is gonna be the terms of K is equal to the delta, things like that, Fk delta, things like that, gonna be another term there, okay. So where the N term is gonna be active coin, okay, from the table 10.1, and N sub T is gonna be the total coin, okay, of the coins, total and active coin respectively. Okay, so therefore you may figure out, okay, the relationship between N and N sub T can be explained based on the configuration. Okay, we have four types of the configuration: plain ends, things like that. Okay, is mean we just wind the coin, the spring, okay, around the post, things like that. Okay, and then cut, okay, in a manner look like that. Okay, with plain, not quite uniform, things like that. Okay, we got plain ends. Okay, and then we just grind. Okay, we just grinding. Okay, the top parts. Okay, of the spring out. Okay, we called it plain and ground. Then things like that. And then another part we squared it. Okay, we cut it square, and then we ground. Okay, we ground it. Okay, at the top part, things like that. Okay, you may ask me which one is the best ever. Okay, I might say, okay, square and ground is going to be the best ever, things like that. Okay, so therefore this is the things that what we show on that. So therefore the relationship between the total coin and the active coin, n equal to n sub t, and n is equal to n sub t minus 1 respectively. Okay, this is the total coin, and the term relationship of delta and the force about, things like that. You can just go for it, whatever. And then, okay, another relationship between, okay, for the static services, things like that. Okay, it's mean, okay, the force is constant, things like that. Okay, we have a figure 10.3 show you, okay, the L sub S is the free length, things like that. Okay, the coin spring is stand still. We have yet applied the force on it. The coin spring is free of the force, things like that. Okay, we apply the force on it. Okay, this one is contraction of delta sub W, things like that. Okay, and then we increase the force of F until the coin spring have been touched to each other. We call it solid force then, F sub S. We call it solid force. The solid force is mean the coin spring gonna be touched to each other, and then it's been contraction in terms of delta S then. And then the length of L sub S is going to be solid height then. It means the spring coil touching to each other as a solid member then. So therefore this mean, okay, this one is going to be solid member, it's not spring anymore. So therefore it's going to act as a member of a workpiece anyway. So therefore this is going to be important here. We never allow the spring to be touching each other. It's going to be some kind of like a workpiece, things like that. So therefore this is the things that what we going to be avoid this kind of thing to be happen anyway. So therefore, the delta S going to be equal to L sub F minus L sub S respectively. So in order to avoid the spring to touch to each other, things like that, or we call it cache allowance. The cache allowance or R sub C, typically we're gonna provide about 20% then. Okay, it's gonna be delta S minus delta W over delta W respectively. So therefore, this is the estimation of the feeling that what we recommend to do on it. We're going to have a plane N. The feeling is going to be equal to P times N plus D. N sub T, that's what I talked about it already. And the solid type should be like that. Okay. So another one. Okay. Since we have the total coin, things like that, we're going to have a force applied on it equal to K times delta, things like that. We just make a substitution, okay, of the terms, things like that, based on the form equation of the valve equation, we're going to have the relationship of the total things show you on like that, okay? And then for the allowable shear stress of the spring valve, things like that, recommendation for the tile design, okay, of the spring, things like that, is going to be on table 10.4 for the hot drawn valve, things like that. We're going to have for the light services, is mean the load applied less than 10 to the power of 4. For the average services, going to be 10 to the power of 4 to the 10 to the power of 6, going to be about the million, 1 million life cycle, things like that. Okay, serious services going to be 1 million, 1 million lifetime, things like that. Okay, so therefore, this is a stainless steel, things like that. Okay, that's what we're going to have a services, things like that, very recommended to be look like that, okay? And then this is gonna be the SI standard, okay? The spin will be available there, so that's why if you come closer to any value in here, you make a selection of the spring one, whatever you want to. That's gonna be feel free to make a selections on that and what. Okay, let's go for example here. Example 10.1 uses design on a helical compression coil spring to obtain a contraction of 10 millimeter with an axle loading of 100 Newton. Given that the spring Y is made of hot-drawn YSTM A227, the cash allowance of the coin spring R sub C is 20%. Utilization can be classified as light services. The free length of the coin is L sub F is 24 to 28 millimeter, and coin spring has a plane and ground end. Okay, let's go for it. So therefore, this is the hot drawn Y. We just open up table point 1. We got A term and X term respectively. We got the sigma U and then the light service for 10.4. We got town design of 0.344, and then we plug everything back in. We got the tau sub Y, and then we got the C term, okay? Is recommended to be 5 to 10. I make selection in the middle. C is 7. Remember, C is going to be D over D, right? So I just recommend you guys, right? Remember that if C is huge, it mean okay, your spring is large and short, right? So if C is small, it mean your spring is long, right, and slim, right? So therefore, this one I make in the middle, things like that. We can adjust after this anyway. So therefore, we got a K term, look like that, and then I got the tau term. I plug everything back in. I got D equal to 2 point something. So therefore, I have no choice. I got to make a selection, 2 point something. I got to make a choice of 2.0, right? So therefore, I make a choice of 2.0, and then it's given by the prompt set, K equal to F over delta. I got the K term there. I got to plug it in. I switch the side. I got the N term is equal to 5.83, and then I look it up in table 10.3. The total coin n sub t equal to n plus 1. I got it 6.83. And then the solid height I sub s, I got it there. And then I got delta W is going to be 10, things like that. The cash allowance is 20%. So I got delta S is 12. Okay. And the free length, okay, is going to be based on that. I got L sub S plus is going to be look like that, 25.66. So that's why I'm lucky. I gonna be within the length. So therefore, if I'm not within the length, I can adjust the C term back in there, right? I can just get back here. If it's shorter, I can adjust the C term, whatever I want to. If it's longer, I can adjust the C term, whatever I want to. And then this one is very important here, okay? I said here, since the solid stress tau sub s, which is the stress induced in the spring, while when the spring quite touching to each other as a solid member, has to be lower than the shear yield strength of the spring material tau sub y, or tau sub s less than tau sub y. So this is why we're gonna check it over. So this one, you got to check it. Be careful. If you don't check it, okay, I'm gonna make a deduction of your point, 2 points, because it's very important. In case of emergency, in case of accidentally, whatever, okay, you got overloading problem, things like that. Your spring is gonna be safe anyway. So F sub S is gonna be 120. Tau sub S therefore is gonna be look like that, and then tau sub Y is gonna be look like that, and then tau sub S, okay, less than tau sub y. It's going to be safe anyway. See? So therefore, it's just like that. Okay? If tau sub s is going to be greater than tau sub y, you can make adjustment by just adjust the value of c again. See? Everything is going to be dependent on the value of c all the way. See? That's what I meant. Okay? So you got to do on it anyway. Okay? So therefore, everything can be summarized, okay, based on the things that what you can be able to do on it, okay. And they, for the last one, design a periodical coin spring for the fatigue failures, anyway. So of course, the spring never ever, okay, for the static load anymore. It's gonna be load gonna be changed with time, of course. So therefore, Solver criteria going to be applied on the helical spring. So therefore, the equation of Solver can be applied on it as 1 over n tau sub m minus tau sub a over tau sub y plus 2 times tau sub a over tau sub n respectively, where tau sub n is going to be equal to this equation and tau sub m is equal to say this equation, where you may figure out this is k sub s respectively. So therefore, let's see the example. Cam and follower are to actuate the linear motion of a mechanical linkage below. The follower is held constant, okay, against the cam by a vertical compressor spring with a force that vary between 300 to 600 as the spring length value over the length of 25 millimeter ends are to be square and ground. So therefore, the spring is made of R tempo YSM A229, given the cash allowance 20%, and the free length is L sub F is 150 to 200, and the safety factor N is equal to 2, determine the standard size of the spring Y and related term. Okay, so therefore you may figure out, see the load is changed with time. So the load is constant, so it changed with 300 to 300. So therefore, the contraction is going to be 25 respectively. So therefore, we're going to design with the fatigue design. So we're going to look up in the table 10.1. A is going to be 1855 and B is 560 and A is 0.19, Y is 0.634. We find sigma U tau sub N tau sub Y, and then we find F sub M, F sub N, and then C term, I do another way around rather than the things that what we have done before. I just fix, okay, I make choice for the C term, it's 6, okay, let's see. And then I find the K term, I find the K sub S, I find the tau sub M and tau sub N, and then I just plug everything in the Soderberg equation. I just do the trial and errors. I find the diameter is going to be 7.2. I look up in the tables of the standard Y. I make a selection of D. Okay. So therefore, I just find the diameter of the capital D there, and then I just make a selection. Look at me. I just trying to find the L sub S is given by the problem set to be 150 to 200. Okay, the SFF, right? So therefore the contraction is 25. So therefore the minimum is going to be what? 150 minus 25 is going to be 125. So therefore I should be less than 125, right? So I just find the L sub S I assume to be less than 125. I make a selection of 120 anyway. So therefore I go ahead with that. I just make selection of table 10.3, I find L sub S, and then I find the N term, I find the 10.3 again, I find the N sub T, okay? And then the load is changed with time, change from 300 to 600, the contraction is going to be 25. So therefore, I find the K terms there, and then I find there the W, I find the sub C is given by the problem set 20%. I find the delta S there, and then I find the L sub S. It's going to be sure that within the feelings that what I need, 180. Okay, I find the F sub S there, and then find tau sub S there. I check it over, so that's why I self. Okay, with the tau sub S, it's going to be less than tau sub Y. I find the rest of that. That's going to be my answer. Okay, is going to be it, okay, for the calculation, for the helical compressive spring anyway, okay? All right, so I can stop for a while.